Okay, so I just wanted to give a few hints on assignment 5, question 1. Let's see. So basically we want to prove that this equation has a solution. Okay. Let's call first, basically that means we want to show the column space of R transpose R is equal to the column space of R transpose. If that's true, this is like just some vector in the column space of R transpose, and if these two column spaces are equal, well then this vector is in the column space of R transpose R, which means you can write it as R transpose R X, some X. Okay, and in fact we always have that column space of AB is contained in the column space of A. Okay, so W is a subset of R. We just want to show that, or sorry, W is a subspace of U. We just want to show that U is a subspace of W. One way to do that is to, well, like W and U are the column spaces of two matrices. We can compute the dimension of the column space by the rank nullity theorem, like dimension of column space plus dimension of the null space equals, I guess it just equals the number of, I guess, columns. Okay. So in particular, if we can show that the null space of R transpose is the same dimension as the null space of R transpose R, will be done, because then their column spaces have to have the same dimension too. Okay. So basically what we want to do is show this. Okay. So if we know that Rx equals 0, then it is immediate that R transpose Rx equals 0. So we have this direction. Easy. Okay. So let's suppose R transpose Rx equals 0. And that means for all Y transpose R transpose Rx equals 0. Oops, sorry, this is the number 0. Okay. And in particular, you can take Y equals X. In particular, X transpose R transpose Rx equals 0. Okay. But now X transpose R transpose Rx, that's just Rx transpose Rx. That's the dot product of Rx with itself. That's the norm squared of Rx. The norm squared of Rx, that equals 0 if and only if Rx equals 0. So if R transpose Rx equals 0, then Rx equals 0. Okay, that tells us that the null space of R transpose equals the null space R transpose R. Therefore, their column spaces are the same. Column space of R transpose equals column space of R transpose R. And that's what we wanted to show. Well, now, just to reiterate, R transpose QB, or R transpose Q transpose B, that is just some vector in the column space of R transpose. Since column space of R transpose equals column space of R transpose R, some vector in the column space of R transpose R is equal to this, and that's what this represents. Okay. I also wanted to give you a hint, at least a little bit for the second two parts of this question. So basically, we want to compute the inner product, or sorry, the dot product of AX0 minus AX. So dot product, well, dot product just means take transpose, and with AX0 minus B. Okay, so all we do is we take transpose and multiply it out. So let me just start that process for you. You get X0 transpose A transpose AX0. So I've taken this times this, then minus X transpose A transpose AX0. That's this times this. Then we do this times this. Minus X0 A transpose B plus X transpose A transpose A. So I did this times this, and then I would do this times this. Oh yeah, so that would be B. Okay. Okay. And now just so either, so just rewrite R transpose R as R transpose Q transpose QR, because the columns of Q are orthonormal. Or yeah, okay, so and then this becomes A transpose A. Okay, for example. And then use part A, and then for the last part, well, once you show that these two things are orthogonal, you just use I'll just write it down as a fact, and it's fine if you do too. Okay, if V is orthogonal to W, then norm squared of V plus W equals norm of V squared plus norm of W squared. Okay, so, and that's only true for orthogonal vectors, right? I mean, if you think about it, this is like the Pythagorean theorem. Okay, and now try, well, what happens? So you write AX minus AX0 as V, and AX0 minus B as W, and you write this as greater than or equal to W squared. Okay. And that is just a few hints.